Hello. This presentation, which I hope to keep brief and to the point, concerns the subject of the standard error of the estimate, which is a subheading under the general topic of validity of tests and measures. So here we go. Right. So again, this is primarily intended as a how-to guide, but also will be covering, what is this all about and, who cares, that sort of thing. So the standard error of the estimate. We always need to remember that when we predict an outcome, there is some degree of random error that will plague us no matter what. None of our tests, none of our predictive formulas have anything like perfect validity. So, I may have some information about you and it leads me to predict that you as a student will earn a 3.58 GPA, but I don't know that you're going to have a 3.58 GPA. There's some degree of error built into that, and that's what we want to estimate here. So again, what I've got is a point prediction based on some assessment, which is an approximation of the truth. And so the standard error of the estimate is the statistic that tries to capture or represent the degree of uncertainty that's built into my prediction. And yeah, if you would think back to when you were studying reliability, this is an awful lot like the standard error of measurement, only instead of talking about the reliability of a test and whether a test score is close or not so close to what the score should be. Here we're speaking of the validity of the test and actually forecasting some other variable. So, getting it. We only really need a couple of pieces of information here. In fact, one of the challenges sometimes is that we will always have more information available to us than we need. And we have to identify which are the points that we do actually need here. So one of the things we actually need to know is the strength of the correlation between our test score, which we're using as the predictor, and whatever the criterion measure is, the outcome. In other words, what we want is some kind of validity coefficient. As a side note for more advanced students, if you're looking at a regression equation, the beta weight is equivalent to a correlation coefficient and could be used in lieu of it. Okay, the other thing we need is the standard deviation of the outcome, not of our test, but of whatever it is that we're trying to predict. Those are the only two pieces of information you need. And the equation for the standard error of the estimate, S sub EST, so I'm representing it here, is the standard deviation of the outcome, SD sub Y, times the square root of the quantity, 1 minus the squared correlation between predictor and outcome, between test and criterion. So calculating it, that was a big mouthful just then, but we'll walk through it, of course, step by step as we do. So we have our equation. We can look at it all day if we want. So the first thing I need to do is to square that correlation. The second thing I need to do is to subtract whatever I get from 1. Then I take the square root of what I got in step 2, and then I multiply it times the standard deviation of the outcome. And that is actually it. So the two things to remember that are important, because it's very easy to mess these up, are first, we do need to square the correlation. Now I'm emphasizing that because if you've grown accustomed to calculating the standard error of measurement, you're used to not squaring the reliability coefficient. Here you do. Just a small difference, but it can lead to substantial errors in our calculations. And the second thing, as I've already said, is it's the standard deviation of what we're trying to predict, not of the test. One way that this may help some people to keep it straight. Imagine you're using like an SAT scale, where the mean score is like 500 and the standard deviation is 100. Theoretically, it's usually close to that in practice. And we're using that to predict a GPA, which is on just a 5-point scale, right? 0 to 4. If you used the standard deviation of the SAT in your prediction, you'd be saying that the standard error of the estimate would be something, depending on how valid the SAT is, something on the order of 60, 70 GPA points. But there aren't 60 or 70 GPA points. There are only 5. So the standard deviation couldn't be more than like 2. So again, it's, we're thinking about what we're trying to predict here, not about the test itself. So walk through an example, of course. So say we are prison psychologists, and we've run a study of the outcome for 200 inmates. These inmates were released on parole, and before they were released, we administered to them the Hare psychopathy checklist. So we know as a predictor how psychopathic they are, and then we follow them up for the next 2 years to see how many times they're either arrested or have parole violations, things like not showing up for a meeting with your parole officer. And we find the correlation between psychopathy score and the number of violations is 0.45. On average, our former inmates have 15 of these sorts of events over 2 years, with a standard deviation of 4. So if in the future I want to use the Hare psychopathy checklist to predict problems post-release, what is the standard error of the estimate? You see how this would be a very important thing in practice, right? All right, well, again, we walk through it. 0.45 times 0.45 is 0.2025. Subtract that from 1, we get 0.7975. Now, incidentally, if you want to round off further than this, that's fine. Unless you have a statistics professor or a psychometrics professor who's extremely strict about the degree of precision, then do what she tells you to. Anyhow, the square root of 0.7975, which again, I would be pretty comfortable rounding off to 0.8, is 0.893. All right, so I multiply that times 4, the standard deviation of the number of parole violations, arrests, and so forth, and I get 0.3572, so I could say 3.57 or 3.6. So if I make a prediction about how many parole violations you're going to have, there's that much play around it, so to speak. We'll come back to that shortly. So we're going to do one more slowly together. And so here we'll do something a little happier. We have students applying to an MFA program, specializing in painting, and we want to have some estimate of how successful they're going to be. And we're going to, as an estimate of that, we're going to use how many paintings they submit to juried exhibitions during the 3 years of the MFA program. So we know that on the creativity test, the mean score is 100, standard deviation is 20. That's how it's been normed out. And we know from past experience that the average or mean student in the program submits 12 paintings over the course of 3 years, but there's a large standard deviation around that, 8. Okay, and we've done a study and learned that the correlation between the creativity test and the number of paintings submitted is an impressive 0.64. Again, make-believe data here. I don't know of any creativity tests that would be that powerful at predicting something like this, but one can always dream. All right, so what is the standard error of the estimate? Now, the first thing you have to realize is there's a lot of information here that would always be available to you, but that you don't need. All you really need is this number and this number. So, in fact, let's walk through it in with the calculator just to see what we get. Okay, so here we have our handy dandy calculator, and we would say, all right, 0.64 times 0.64. I could have just used the squared key there, of course. 0.4096. And I'm going to round off a little bit to 0.41. So step 2, right? And you can be doing this along with me. Maybe you've already got the answer for all I know. 1 minus 0.41, close to 4096, gives me 0.59. So now I know that the answer should be 8 times the square root of 0.59. So I hit the square root key. Ooh, I get a big long thing. Let's round that to 0.768. I'll just multiply. We'll see what we get. Times 8, the standard deviation. So it's about 6.14. And again, if I'd rounded, I might have gotten 6.15 or 6.16, but it would be very close to the same thing there. So there, again, notice there's quite a bit of play here. We'll come back to that. Because the fact is that the behavior of individuals is hard to predict. We're trying to predict very complex things like, how many times you're going to get busted in the next 2 years? How many competent paintings are you going to produce and be willing and able to send out to juried art shows in the next 3 years? I don't care what test you have, these things are going to be hard to predict. Now, in research context, what we often do is to put together multiple predictors. So if I find that there are 3 different things, each of which has some validity at predicting an outcome, I can put them all together in some cases using a kind of procedure called multiple regression. That goes beyond anything I'm covering in a statistics or psychometrics class, but it's important for those of us reading journal articles to realize that this is a frequent procedure. So the idea is that if I have multiple predictors, each of which has some validity, I'm going to have a more highly valid or more accurate prediction possible by putting them all together. So to take an obvious example, if I'm trying to predict how well someone's going to do in college, yeah, well, high school grades are a pretty good predictor. SAT scores have add some incremental power to that. And maybe the personality trait called conscientiousness, basically how much people actually do what they're supposed to do, should be added in. And if I have all 3 of those, maybe I can do a better job of predicting your success in college than I could with any one of them. But we'll move from there. So, confidence intervals. Some people love them, some people hate them. But the fact is that just as we could construct confidence intervals around a test score using the standard error of the measurement, similarly, we can construct confidence intervals around a prediction based on the standard error of the estimate. It works exactly the same way. So there's nothing new here if you've already learned how to do this in the context of the standard error of measurement. So for example, if I wanted 95%, the 95% confidence interval around a predicted score, that would be the range from 2 standard errors below the score we got up to 2 standard errors above it. And this is all just that normal curve thing. If you're within 2 standard deviations, in this case, it's the standard deviation of the errors in our predictions, the errors in our estimates. The difference, of course, from standard error of measurement is that, again, we're speaking of predicted outcomes rather than qualities inherent to the test itself. So how well will you do in law school? How soon will this patient relapse after discharge from the hospital? Those sorts of questions. Calculating them, look, it's exactly like doing it with the standard error of measurement. So I'll walk through it real quickly, but for more detail, there's a presentation on that you can review. You just need the standard error of the estimate, how confident you want to be, that's your choice, and the table displaying the area under the normal curve so you can look it up on the table. That's it. And all you do is use that table to find the multiplier. I'll show you that again. Multiply it times the standard error of measurement, and then you take whatever the prediction is and you subtract it. There's the lower bound estimate. Add it to what you got. There's the upper bound estimate, and that's it. So the multiplier, this is a simple table to use. You can find these in any statistics book all over the internet, your call. But let's just say I wanted 75% confidence intervals. I want to have 3-to-1 confidence that this range of values contains the true outcome for how this art student will do or how this released ex-convict will do. Okay, well, I take this column Z to mean and I go down until I find something close to half of that 0.75 value. So I'm looking for something like 0.375 and happens to be pretty much right in between here. So what I'll do once I find it is just go over to the left to the Z column. The Z column contains what will be my multiplier. So I'm about halfway between these two. So I'll just say 1.15. So as an example, Wackford Squeers is going to be eligible for parole next month. He was in for brutality to children, and his score on the psychopathy checklist predicts that he'll have 22 parole violations in the next 2 years. So what are the confidence intervals around this? Well, we had calculated the standard error of the estimate earlier. It was about 3.57 or 3.6, and we just looked up the 75% confidence intervals. So all I need to do is take that standard error of the estimate and multiply times 1.15, I get 4.1. So let's just round it off to 4 because parole violations, arrests, they happen or they don't happen, right? So the predicted 22 minus 4 is 18. That's the lower bound estimate. 22 plus 4, 26, upper bound. So the 75% confidence interval is 18 to 26. So we are confident at 3-to-1 odds that he's going to have more parole violations than the average person being released, which was 15. So we, depending on where we decide to set the threshold, and as the prison psychologist, that's up to you really, in consultation with other authorities, we would probably say that Wackford Squeers is a bad risk for release at this time. We'll do one more together for practice. So we have Philip Carey, who's aspiring to a career as a painter and applying to art school. He takes the creativity test and his score suggests that he's going to exhibit about 10 paintings over the course of the 3-year program. And let's just say we want a 68% confidence interval around this, because that's just the multiplier then is 1. Let's just make life easy. So we had calculated the standard error of the estimate earlier, and here I think we got 6.14, but I must have rounded off sooner time before. So we'll say 6.16, but it's about 6 basically. So what are the 68% confidence intervals? Well, again, here what makes it simple is that we don't have to multiply really, do we? Because multiplying times 1 just gives you what you started with. So we would say, well, we predicted 10. So it's probably going to be somewhere between 10 minus 6, 6.1, 4 or 5 or 6, say 4, up to 10 plus 6 or 16. So he's probably going to exhibit somewhere between 4 and 16 paintings. Whether that makes him a good candidate for the art school is up to the standards that we've established, right? So if we have said that we don't want anyone whose 68% confidence interval drops below 0, we don't want anyone who's not succeeding in submitting anything to a juried art show, he's in good shape, right? But again, those decisions are made not mathematically, but for other reasons. Now, again, predicting individual cases is tough, right? I'm sure you've noticed there's a lot of play around these predictions. That's life. The standard error of the estimate, unless we have astonishingly good predictors, tends to be larger than we would like it to be. That's just the way life is, right? Even with highly valid tests, you're not going to make exact predictions for individual outcomes that come close to being exactly right most of the time. You can do a much better job predicting group level behavior, but individuals, again, it's tough. Nonetheless, we've improved on random prediction in 2 ways. One is this: If I know nothing about you, if I have no prior knowledge of you, and I'm asked, how are you going to do at something? All I can really say to minimize how wrong I'll be, and I'll be very wrong most of the time, but all I can really say is you're average. Your IQ is 100. If you're a man, American man of today, you're about 5'9" and weigh about, I forget what the average is, 175, 180 pounds or something. That's all I can do because I have no prior knowledge. Whereas with a test, we're generating a point estimate that is not usually right at the average. So I could be saying, well, based on the test, I think your IQ is 122. That's a very different prediction. And we have also shrunk the margin of error, so to speak, a bit. Going from a standard deviation of 8 to a standard error of the estimate of 6 is tightening things a bit. So we've made gains in 2 ways. Now, wrapping this up, the standard error of the estimate, again, simply represents how far random error influences, how extensively random error influences the outcomes you're trying to predict based on whatever kind of assessment procedure you're using. Once we know the standard error of the estimate, we can construct confidence intervals around the outcomes we're predicting, which enable us to have these little ranges and be confident, to whatever degree of confidence we insist upon, that the true outcome is going to be in that range. But always remember that our power, our technology here is limited in its ability to predict the behavior of individual people. There's always quite a bit of error built in there. And the more advanced note I threw out partway through the presentation is worth remembering that sometimes if we put together a series of predictors that are not all the same thing, but each of which has some ability to validly predict an outcome, we can do a bit better. And I think that is going to be a good place to wrap it up. So I shall say good day, and we'll see you again for another episode.